Okay, in today's video, we're going to go over an explanation of what is escape velocity. Now, I'm just going to start off by giving you the definition, and we'll use that definition to kind of come up with our explanation, our understanding of what escape velocity is. Okay, escape velocity is the lowest velocity that an object must have to escape the gravitational attraction of another object. And really, it's the lowest initial velocity. So we're going to take something and project it, apply a force to it, and give it some initial velocity, like when we kick something or shoot something or launch a rocket up into the air. What's the lowest velocity that it could have initially at the surface of the Earth and still escape the gravitational attraction of the Earth, for example, or of the other object? Now, in order to come up with this, we are going to use the idea of conservation of energy, the conservation of total mechanical energy. Well, that means that the initial total mechanical energy has to be equal to the final total mechanical energy. Now, how we come up with the idea of escape velocity, I think is very interesting, and it's more interesting than just what is the escape velocity, because we can just look that up. You can look that up anywhere. The escape velocity for the Earth, I believe, is like 11.1, 11.2 kilometers per second. But what does that mean, and how do we come up with that? That, I think, is the most interesting thing, that you can explain to somebody what escape velocity is. Now, we're going to use, as I said, conservation of energy, and conservation of energy for total mechanical energy is really the kinetic and the potential. So that means the sum of the initial kinetic and the potential is equal to the sum of the final potential and kinetic. And now we're going to use this definition to simplify this equation and come up with the equation for the escape velocity. Now, it says here that it's the lowest velocity that an object must have. Now, when the object is sitting on the surface of the Earth, we know it already has some potential energy, which we calculate as minus g times m1 times m2 divided by r, which we'll talk about that in just a moment. So it already has some initial potential energy, or some potential energy when it's sitting at the surface of the Earth. And this says the lowest velocity. It's really the lowest initial velocity, and that's inside that kinetic energy, because the kinetic energy we all know is 1/2 mv squared. It's really 1/2 mv initial, which is actually the escape velocity, that's what we're going to be solving for, the velocity that's inside that kinetic energy term. Okay, that's the lowest initial velocity in there. Now, it does say here then that the object must have to escape the gravitational attraction. Well, how do we know it's escaped the gravitational attraction? When has the object escaped the gravitational attraction? Well, it has escaped the gravitational attraction of another object when the potential energy is 0. So that means when that term is 0, it has escaped the gravitational attraction. Or when it has escaped the gravitational attraction, then that term is 0. Well, how do we get it to escape the gravitational attraction? We got it to escape the gravitational attraction by giving it some initial kinetic energy. Well, what happened to that kinetic energy? Well, that kinetic energy was used to overcome the gravitational attraction. So when there's no gravitational attraction, then that means all the kinetic energy has been used, and that means that the kinetic energy, the final kinetic energy, is also 0. Okay, that's the lowest. Now, we could give it more, and it could still have 0 potential energy and have some leftover kinetic. But because it says here what's the lowest would be how much we need to get it to escape that gravitational attraction. And when it's escaped the gravitational attraction right at that point, then it has no more kinetic energy in it also, because all that energy has been used to overcome the gravitational attraction. Okay, so that, I think, is really the most interesting thing about the whole thing. Now really we're just going to derive the equation. Okay, so now what we're left with our conservation of energy is that the initial potential plus the initial kinetic is equal to 0. Now all I'm going to do is I'm going to subtract the potential energy, the initial, from both sides, and I get that the initial kinetic is equal to minus, don't forget the minus sign, it's very important, minus the initial potential. Okay, we're going to go to the next slide, and now in here, as we said, we have our initial kinetic energy, the lowest possible velocity. And here's our initial kinetic, and inside there is the velocity, because we all know that kinetic energy is 1/2 mv squared, and it's the initial, this is the lowest term, this is really the escape velocity. And that's equal to minus. Now this minus is this minus. Don't forget your minuses, because we have another minus because the equation to calculate the potential energy is also minus g times m1 times m2 divided by r. Now, just to simplify this really quick, we get that 1/2 mv squared is equal to now g. A minus is a plus, so now we have no more negative signs. But we do have this mass, and this is the mass of the object when it's getting ready to move, when it's moving with its initial velocity, and this is the mass when it's staying on the surface of the Earth, so those masses are the same. That's the object of the mass. That means those two cancel. And that means we're left with now 1/2 the initial velocity squared times g m1, well, g times m1 divided by r. Now I'm going to solve for this. I'm going to do this all in one step. I'm going to do two things. I'm going to multiply both sides by 2 to get rid of the 1/2. And then I'm going to take the square root to get rid of the square here. And I get that the initial velocity, which is really the escape velocity, that's the escape, is equal to the square root of 2, because I multiplied both sides by 2. And I took the square root of both sides, so it's 2, it's the square root of 2 times g, the gravitational constant, times m1, the mass of the central object, divided by r, which is the distance between those two objects. And if we're talking about Earth, then this would be 6.67 times 10 to the minus 11, that's the gravitational constant. This would be the mass of the Earth, 5.98 times 10 to the 24th. And this is the radius, the distance from the center of Earth to out to the object. Okay? So actually, we're going to do that in the next slide. This is the equation. I put a box around it. Put a box around. Don't forget that. I'm going to calculate the escape velocity of the Earth. Okay, everybody knows 2 is 2. The gravitational constant is 6.67 times 10 to the minus 11th Newton meter squared kilogram squared. This is the mass of the Earth. This is gravitational constant. This is the mass of the Earth, 5.98 times 10 to the 24 kilograms. And r, as I said, is the radius, and it's actually the radius of the Earth because the object is sitting on the surface of the Earth, and it's the distance from the center of mass of the Earth, which is the center of the Earth, out to the object, which is basically sitting on the surface of the Earth, so that's just the radius of the Earth. It has to be in meters, so this is kilometers. The radius of the Earth is 6,371 kilometers. We want to convert that into meters, so I'm going to multiply by 1,000 times 10 to the third, that's 1,000, and you just do all that math, and you get that the escape velocity is 11,189 meters per second, which of course is basically 11.2 kilometers per second. So if I can take something, and throw it, project it, launch it with an initial velocity of 11.2 kilometers a second, then that object would escape the gravitational attraction of Earth. And when it escaped the gravitational attraction of Earth, it would stop moving because it would have used all of its kinetic energy to overcome the gravitational attraction between those two. Now that, of course, does not take into account the friction from the Earth's atmosphere and all that other kind of fun stuff. But theoretically speaking, if we ignore friction, the escape velocity is 11.2 kilometers per second. Okay, so there you go. Now, I hope I impressed upon you some of the interesting things about what escape velocity is and how we come up with the equation for escape velocity, and not just what escape velocity is, because you can just look that up, okay, for any planet on Earth and for the sun and things like that. Okay, so there you go. Hope you found it helpful. If you did, please do all the following 4 things. Once again, subscribe to my channel again. Get all my excellent physics, chemistry, and math videos again. Leave me a thumbs up for this video, and leave me another nice comment in the comment section. And don't forget, once again, that sharing is caring. Share this video and show all of your friends how much you care about them. Thank you very much for watching. We'll see you in the next video.